Hi everyone, this is lesson 2-2, polynomial functions. Our learning target is going to be for students to be able to find repeated zeros of polynomial functions. In example 5, we're going to talk about polynomial functions with repeated zeros. In this question, we're asked to state the number of possible real zeros and turning points of h of x equals x to the fourth plus 5x cubed plus 6x. This is the equation we're given. And then we're going to determine all of the real zeros by factoring. So what we're going to do here is we are going to try and find all the real zeros of this function by factoring. So if h of x is equal to x to the fourth plus 5x cubed plus 6x squared, first of all, the zero of a function is also known as its x-intercept. And the way we find our x-intercept is by substituting 0 for y. So I'm going to substitute 0 for y, which is also h of x, function notation. And I am going to then factor the right side of the equation. First of all, I can see that these three terms here, x to the fourth plus 5x cubed plus 6x squared, have a common factor of x squared. So there's two x's that I can factor out of each term. And if I factor out an x squared in front, that leaves me with, on the first term, x to the fourth, that leaves me with x squared. Because if I were to distribute the x squared back in, x squared times x squared is x to the fourth. Now, what I'm going to do from here is I'm going to factor out an x squared from 5x cubed. That leaves me with 5x. And if I factor out an x squared from 6x squared, that leaves me with a positive 6. From here, I'm going to factor the trinomial that we have left inside the parentheses. So if I'm thinking about factoring x squared plus 5x plus 6, I need to find the numbers that multiply to be 6 that add to be 5, which is going to be 3 and 2. So I'm going to factor that trinomial, that quadratic trinomial, as x plus 3 times x plus 2. Now, if I were to factor x plus 3 times x, not factor, if I were to FOIL x plus 3 times x plus 2, I would get x squared plus 5x plus 6. So what we have right here is a polynomial in factored form, and in fact I could break up the x squared as x times x, and then I have times x plus 3 times x plus 2. And from here I have 4 different factors, and since I'm multiplying them all together and my product is equal to 0, I know that the only way to get a product that's equal to 0 is if one or all or some of the factors are equal to 0. So I'm going to account for all my possible zeros by setting each factor equal to 0. So I get x equals 0 and x equals 0 on the first two factors. Here, when x plus 3 is equal to 0, that means x is equal to negative 3. And over here, x plus 2 equal to 0 is equal to x equals negative 2. And from there, I have 4 zeros for this function. Now, as you can see, this 0 here, x equals 0, occurs twice. So when I list the zeros of my function, I actually only have 3 unique zeros for this function. They are x equals 0, and I'm going to state that x equals 0 has a multiplicity of 2 because it occurs twice. And x equals negative 3 and x equals negative 2, I don't need to state a multiplicity for that because they don't repeat themselves. They don't occur more than once. So my 3 zeros on this function are 0, negative 3, and negative 2, And that's the reason I say there's 3 zeros instead of 4, like I circled in red up here, is because x equals 0 occurs twice. So I'm only going to list that one time and state that its multiplicity is 2. Now, one thing I didn't address at the beginning was how many possible zeros this polynomial could have. Now, the reason, or the way we find the possible number of zeros a polynomial can have is by its degree. And again, we've talked about this in a previous video. The degree is the highest exponent in the polynomial, and in this case, that degree is equal to 4. So we have a degree equal to 4, which means the possible number of zeros this function can have is equal to 4, because that's always equal to our degree. And the number of possible turning points, I'm going to say possible because it doesn't mean we'll have exactly that number of turning points, is equal to 1 less than the degree. So if I subtract 1 from the degree, I get 3 possible turning points for this function. So I want to keep these things in mind when I go to graph the function. When I look at a polynomial, before I even find its zeros, I should look at the degree and say, okay, this polynomial can have 4 possible zeros. So when I'm doing my factoring, I should be looking for 4 zeros, and it'll never exceed that amount. It could be less than that. It could be less than 4 zeros. In this case, the last example had only 3 zeros, and it's because one of them was repeated twice. So it had 4 zeros per se, but there were only 3 unique zeros. So when I look at that, remember, when we actually found the zeros, we got x equals 0, x equals 0, x equals -3, and x equals -2. And again, just to reiterate, we only had 3 unique zeros because 0 is repeated, and therefore x equals 0, -3, and -2 are our actual x-intercepts on the graph. Okay, so here we are at a check for understanding, and I want you to try this example on your own. I want you to state the number of possible real zeros and turning points for the function g of x equals x to the 4th minus 4x cubed plus 4x squared, and then determine all of the real zeros by factoring. Of course, we have a multiple choice question here, A, B, C, and D. You can use your test taking strategies that we've discussed in class, such as eliminating answers that you know are incorrect, before you go ahead and work out the solution. And then I want you to check or choose the correct response and press submit. So go ahead and pause the video now, work out this problem, and submit your answer. Okay, so in the last example you were asked to solve or find the possible number of zeros for this polynomial function and the number of possible turning points. Well, if I look at my degree, which is the highest exponent, my degree is equal to 4. So we have a degree 4 polynomial, which means that we have 4 zeros, because the number of possible zeros, I should say, it's possible that we have up to 4 zeros for this function, which is always equal to the degree. And the possible number of turning points is equal to 1 less than the degree, which if I subtract 1 from the degree, I get 3. So now that I'm aware of how many possible zeros and turning points this function can have, I'm going to go ahead and factor this polynomial to actually find the zeros. So if I look at x to the 4th minus 4x cubed plus 4x squared, and it's set equal to 0 because the zeros of a polynomial are its x-intercepts, and we learned at the very beginning of the year that to algebraically find your x-intercepts, or your zeros of your function, you substitute 0 for y. Now I'm going to start by factoring out a common factor amongst all these terms. I'm going to factor out an x squared, from each term, and that leaves me with x squared minus 4x plus 4. And I'm going to go ahead and factor this quadratic trinomial, which if I factor that quadratic trinomial, I am looking for the numbers that multiply to be positive 4, but add to be negative 4. So I can start out by separating the x squared as x and x, and when I multiply to be a positive number, but add to be a negative sum, I need minus in both of my factors here. So two negatives multiply to be a positive, but two negatives are going to add to give me a negative, and those two numbers are negative 2 and negative 2. Negative 2 times negative 2 gives me positive 4, but when I add negative 2 to itself, I get negative 4. So, moving forward, I'm going to separate out this x squared as x times x, and then I have x minus 2 times x minus 2 equals 0. And then if I set each factor here equal to 0, I get x equals 0, x equals 0, x equals 2, and x equals 2. So I have 4 zeros here. However, I really only have 2 unique zeros because if I look at my graph, it's only going to cross at x equals 0 and x equals 2 because 0 is a repeat and 2 is also a repeat. So each of these zeros actually has what's called a multiplicity of 2 because each of those zeros occurs twice in my factorization. And when I find the zeros, I can see that each of these zeros, x equals 0 and x equals 2, occurs twice. So if I look at my answers, A, B, C, and D, the answer that represents what I've written down on this slide is answer A. You should have answered A to this question, and if you did, you had the correct response. Now, if you made a mistake, compare my work on this slide with your work and look for where you might have made a sign error or multiplication error, or where you might have made a mistake in getting a different solution than I did. Alright, so we're going to talk more about repeated zeros of polynomial functions here. And there's a lot of big words in this definition or key concept here. One of them that should be familiar from the last two slides is multiplicity. And I want to talk about, I don't really care so much about this definition up here, but I want to talk more about these 2 bullet points down here. We've already discussed that multiplicity is a word that describes the number of times a 0 repeats itself in a polynomial. Now, if a 0 C, they're just being general here, C could be 3, it could be 2, it could be 10, negative 1. If the 0 has an odd multiplicity, then the graph of that function crosses the x-axis at C, and the value of f of x changes signs at x equals C. If we go further than that, if a 0c, so again, if a 0 of a function has an even multiplicity, then the graph of f is tangent to the x-axis at x equals c, and the value of f of x does not change signs at x equals c. Now, for instance, the last example, we got x equals 0, x equals 0, x equals 2, and x equals 2. Those were my 4 zeros. Now, because 0 repeats itself twice, it has a multiplicity of 2. And because x equals 2 repeats itself twice, it also has a multiplicity of 2. Now, where that lies in this definition is right here. When it has an even multiplicity, so 0 has an even multiplicity because 2 is an even number, and 2, x equals 2 has an even multiplicity because 2 occurs an even number of times. So, what we can see at this graph of this polynomial, if we were to graph that polynomial from the previous example, we would see that that graph is tangent to the x-axis. The word tangent means to touch. So the graph actually only touches the x-axis at both x equals 0 and x equals 2, rather than crossing through the x-axis. So I know that many of you have talked about what constitutes an x-intercept rather. And if I just think about the graph from the previous example, I see that I have zeros at x equals 0, which means I have an x-intercept at x equals 0, and I have another one at 2. Now, I know because the lead term in the previous example was x to the 4th, and it was 1x to the 4th, I know from the leading term test that my end behavior are both pointed up. My end behaviors are both pointed up. Our exponent's even and our lead coefficient's positive, which means both ends are up. Now, what's going to happen is because we touch at that x-intercept here, and because it's an even multiplicity, rather than crossing through the x-axis at 0, I'm going to bounce back up, and eventually I'm going to come back down, and I'm going to bounce off the x-axis at 2. And the reason for that is because anytime your 0 has an even multiplicity, the word tangent here means to touch. So all that happens is we just touch the x-axis and then go back in the same direction we came from, rather than crossing the x-axis at that 0 of the function. So odd multiplicity zeros actually cross the x-axis, and even multiplicity zeros actually just touch. This whole word tangent means touch. We're tangent to the x-axis there because we just touch the x-axis and then actually like bounce off of it and go back in the direction we came from. And they also say that the function does not change sign, so meaning that the y-coordinate doesn't change from negative to positive or vice versa there. So we're going to look at some more examples of this. I just wanted to kind of use that previous example to get us started in the definition of multiplicity and what it looks like if the graph has an odd multiplicity versus an even multiplicity. Okay, in example 6, we're going to put all of this together. So the leading term test and the multiplicity and finding all the zeros by factoring, we're going to put it all together in this one example. So we're going to kind of take baby steps towards that. And what we're going to do is we are going to look at this function f of x equals x times 3x plus 1 times x minus 2 squared. And we're going to apply the leading term test. So when we apply the leading term test, though, here's the deal. In factored form, we can't apply the leading term test. So we have to take this polynomial, and x is not our leading term, because the polynomial has to be in standard form in order to apply the leading term test. So what I'm going to do here, I'm going to rewrite this polynomial as f of x equals x times 3x plus 1 times x minus 2 times x minus 2. Now, I could multiply this entire polynomial out. I could multiply, first of all, multiply x times 3x plus 1, which gives me 3x squared plus x. And I could multiply x minus 2 times x minus 2, which gives me x squared minus 2x plus 4. Or, if I simplify, 3x squared plus x times x squared minus 4x, I can combine these like terms, plus 4. And what I would need to do is I would need to multiply this binomial, 2 terms, times this trinomial, because I have 3 terms here. And when I multiply them together, I don't really need to multiply out the whole thing. I can multiply the first term in each function here, or in each factor, And if I multiply the first term, 3x squared times x squared, I get 3 times x to the fourth. So 3x to the fourth is my lead term. So if I analyze that using the leading term test, because my power is even and my lead exponent or my lead coefficient is positive, I know that both ends are going to be pointed up. So what does that mean in terms of my limits? I know that the limit as x approaches negative infinity of the function is equal to infinity. And I also know that the limit as x approaches infinity of the function equals infinity. They're both pointed up, so they're both approaching positive infinity. So these two end behaviors are supported by these two limits that I wrote at the top. Now, in part B, we are going to take this function and we are going to determine the zeros and state the multiplicity for any repeated zeros. Now, here's the thing. Factored form, like the function is given to us, is great when you want to find your zeros. It's not so great if you want to apply the leading term test. So I had to do a little bit of work on the last slide just to figure out what my leading term was. And in this example here, since I want to find my zeros and state the multiplicity, I'm going to go ahead and set 0, f of x equal to 0, because when we find our zeros of our function, y is equal to 0. So we have x times 3x plus 1 times x minus 2 times x minus 2. And if I want to find all my zeros, I get x equals 0, 3x plus 1 equals 0, x minus 2 equals 0, and x minus 2 equals 0. And right here, I have 3x equals negative 1, or 3x equals negative 1, or x equals negative 1/3. And right here, I get x equals 2 by adding 2 to both sides of my equation. And right here, I would also add 2 to both sides and get x equals 2. So I have 4 zeros in my function, but it just so happens that one of them is repeated. The x equals 2 is repeated twice. Therefore, it has a multiplicity of 2. So I do have repeated zeros. X equals 2 is a repeat, but my zeros of my function are x equals 0, x equals negative 1/3, and x equals 2. Okay, so I'm just going to reiterate our final answer here. X equals 0, x equals negative 1/3, and x equals 2. And again, x equals 2 has a multiplicity of 2. So in part C, what they want us to do is find a few additional points on this graph. So far we've determined we have x equals 0, x equals negative 1/3, and x equals 2, which has a multiplicity of 2. And here's what we're going to do. We're going to just kind of plot these points on the graph just to see what we think is going on here. X equals 0. X equals, let's say here's negative 1, negative 1/3 might be right here. And x equals 2 is going to be right over here. Now remember, our end behavior we determined in our leading term test, because our lead term was 3x to the fourth, we determined that both ends were pointed up. So I know from this 0, the farthest 0 to the left and the farthest 0 on the right side, the ends are pointed up. Now, because x equals 2 is a repeat 0 and it has an even multiplicity, I know that at this point right here, the graph is not going to cross through at 2, rather it's going to be tangent at 2, meaning it's going to touch at 2 and it's going to bounce off that x-axis and it's going to come up and it's going to come all the way back down here and it's going to connect at negative 1/3. How do I know that we actually cross through the x-axis at 0 and at negative 1/3? Because they have what's called an odd multiplicity. Its multiplicity here is 1 and its multiplicity here is 1. I don't really feel like you should name the multiplicity here because the word multiplicity means multiples, and there is not a multiple 0 at x equals 0, and there's not a multiple of x equals negative 1/3 either. So, because it only occurs once, we actually cross through the x-axis at these points, and when your multiplicity is even, so if there's an even number of a certain 0, then you are tangent to the x-axis at that point, or at that 0, which means that we don't cross there. So there's two types of x-intercepts or zeros. I like to call them crossing zeros or touching zeros. And whenever you have an odd multiplicity, we cross. Whenever you have an even multiplicity, you touch. So notice that I don't actually cross here at 2. Now, the whole point of this is to find a few additional points. Now, I just kind of sketched what the graph would look like. This is just a sketch. It's not an exact graph. And so what I can do is when I want to find a few additional points, I am going to choose x values that are somewhere in between these zeros that I've represented, and maybe some that are more extreme. So for instance, my smallest x-intercept is at negative 1/3, or my small zero is at negative 1/3. So I might choose a x value a little bit less than that, which is negative 1. Or I could choose negative 2 or negative 3. Doesn't really matter. I just chose arbitrarily x equals negative 1 because it is less than negative 1/3. Then I might choose another x value somewhere in between negative 1/3 and 0, because I have a 0 here at negative 1/3 and 1 at 0. I might want to know where the graph has a relative minimum, or an absolute minimum rather. I might want to figure out where that's at. And so I might estimate somewhere between negative 1/3 and 0. I could maybe use negative 1/4 as my x value. I'm not saying that that's actually the absolute minimum, because we could actually graph the function and find that absolute minimum on our calculator, but I'm just saying it's wise for us to have a point in between an x value, or a point in between negative 1/3 and 0. So I chose negative 1/4. And I need to find an x value in between 0 and 2. And a number in between 0 and 2 that makes sense to me is positive 1. And it could be that this maximum right here, this relative maximum, could be at 1 or near 1. So, in order to figure out what my y-coordinates are, I could graph this function right here, x times 3x plus 1 times x minus 2 squared. And if I substitute these x values in my table, I can find my y-coordinates. That is the fast way to do it. I am going to go ahead and calculate what these y-coordinates are. Okay, I went ahead in Desmos and graphed this function, f of x, and this is a little typo here. This should be negative 0.32, and if we graph this function on Desmos, it looks exactly like what I have almost, because again, on this slide here, I just sketched this based on the leading term test and where my zeros are at, and based on my odd multiplicity and my even multiplicity, whether the graph would cross at those x-intercepts, or actually just touch and be tangent to the x-axis there. So I went ahead and made an additional table of values, and I'm going to plot these points on the next slide when it asks me to graph the function. So they're really scaffolding and putting all this stuff together, the leading term test, finding the zero, finding additional points for our graph besides our x-intercepts or zeros, and now we're going to put it all together by graphing the function. So on the previous page, I looked at finding additional points. Those additional points were at -1, -1/4, and +1, and our zeros were at 0 and 2. Let me take that back. I made a mistake here. I had -1/3 as one of my zeros as well, and -1 is less than that. So my zeros I'm going to circle here were at -1/3, 0, and 2, and my additional points were at -1, -1/4, and +1. So my zeros, I can just fill in 0 for the y coordinate there, because anytime we cross the x-axis or have a 0 of a function, our y coordinate 0. And then I found the y coordinates using Desmos. When I insert -1, +1, and -1/4 rather, into this function, I found the y coordinates. And those y coordinates were 1.8, -0.32, and 4. And I just realized I made a mistake here. This decimal place doesn't belong there. At -1, if I substituted -1 into this function, f of -1 equals -1 times 3 times -1 plus 1 times -1 minus 2 quantity squared, and we get -1 times -3 plus 1 times -3 squared, or -1 times -2 times -3 squared is +9, and -1 times -2 is +2, so 2 times 9 is 18. So there shouldn't have been a decimal there, that's my fault. It's 18, not 1.8. Now what I need to do is go ahead and plot these points on a coordinate plane, and I have the graph of my function. So here is a screenshot of what I put in Desmos. I first of all typed in the equation, and then I hit the table and completed my table with the x values that we had chose, which are our zeros 2, 0, and -1/3. And then I also included our additional points here at -1, -1/4, and +1. And again, the graph, like I said previously, it looks like a W, and we are only touching at +2 versus crossing at -1/3 and 0 due to the multiplicity of our 0. Remember, 2 had a multiplicity of 2, which is even, so we're only going to touch at that x-intercept rather than cross. Here's a check for understanding. I want you to determine the zeros and state the multiplicity of any repeated zeros for the function f of x equals 3x times x plus 2 squared times 2x minus 1 cubed. Now think about the steps that we went through in the last example with the leading term test. Maybe it's good for you to determine what your leading term is here. Start thinking about what your end behavior is, then find your zeros and determine whether any of those zeros are repeated. Okay, and then you can kind of start thinking about what your graph might look like. Even though we're not asked to graph in this example, you might want to think about how the zeros you have and the multiplicity of those zeros impact your x-intercepts, whether they touch or cross, and how that affects the shape of your graph. So go ahead and answer the question and choose a response, A, B, C, or D, and then press submit. Okay, we're looking at this function here, f of x equals 3x times x plus 2 squared times 2x minus 1 cubed. And we want to determine the zeros of this function and state the multiplicity of any repeated zeros. So first of all, we're going to take and set this function equal to 0. So f of x equals 0. Again, y is equal to 0 when we find the x-intercepts of the graph. So we set f of x equal to 0. So we have 3x times x plus 2 times x plus 2. And I'm going to run out of room here. But I also have 3 factors of 2x minus 1. Sorry for the weird 2 here. And if we set each of those factors equal to 0, so we'll set 3x equal to 0, which gives me x equals 0 when I divide both sides by 3. And I have x plus 2 equal to 0, which gives me x equals negative 2. I have another factor of x plus 2, which gives me x equals negative 2. Again, I'm subtracting 2 from both sides here. And then I have these 3 factors of 2x minus 1, which all 3 of those, 2x minus 1 equal to 0, give me a 0 at 1/2. So I would add 1 to both sides, divide by 2, I get x equals 1/2, and that has a multiplicity of 3. Because it has a multiplicity of 3 because there are 3 factors of 2x minus 1, and if we set each of those equal to 0, we would get 1/2 3 different times. Now, this x equals negative 2 has a multiplicity of 2 because it occurs 2 times, and x equals 0 only occurs once, so I guess you could say it has a multiplicity of 1, but I guess it's kind of odd to say multiplicity of 1 when the word multiplicity means multiple and there isn't a multiple of x equals 0. So looking at the answers from the multiple choice, we would get an answer of A, because that is the response that said our zeros were x equals 0, x equals negative 2, and x equals 1/2. And negative 2 had a multiplicity of 2, and 1/2 has a multiplicity of 3.